Okay, so let me quickly remind you what we have seen last week. It was a recorded lecture. I hope you listen to it or you watch it. So we are dealing with discrete time system, and we have seen the iterated map, and most of what we are going to see is about the iterated map, but there is a second type of discrete time system, this one is called the linear difference equation. It's taking place in Rn, and it's just with matrices. So what is it? You take a family of matrices n by n, and you define this equation. A vector at time n+1 is this matrix with index m applied to a vector obtained at time m. So it's a vector is equal to a matrix applied to another vector, but this matrix can depend on time or on m, so it's not an autonomous system. And there is what is called the principal matrix solution. We have already seen something of this type. By doing the product of these matrices between j is equal to m0 and n-1, be careful of the order. They do not commute, so you really have to put them in the right order. By defining this principal matrix solution, you have that if at time n0 your initial condition is x0, you have x of m is simply the product of these matrices. So it's this pi of m n0, defined like this, applied to x0. And if you just think about this matrix, it satisfies this equation, or this family of matrices, it satisfies this relation, which you can directly infer, with the initial condition, m0 is identity. So it's quite simple in this case to write all solutions. And there exists also an inhomogeneous difference equation where you have a second term. This is a vector which depends on m, but again, we have a solution, an explicit solution. So in that respect, the discrete time is simpler than the continuous time, because we can really write explicitly the solution, while it was not the case so explicitly for the continuous time. That's all for this linear difference equation. And then I introduced this logistic equation, which is when it played an important role historically. So you take a parameter r between 0 and 4, and I define a function from 0, 1 to 0, 1, just by this thing which we have already seen in chapter 1, but it was not for an equation of this type, it was for a differential equation, so for continuous time. And for discrete time, I said x at m+1 is this function applied to xm. But x now is just a vector, it's just one value. It's a 1D iterated map. And I've mentioned these cobweb plots. If you have never seen them, please look at the notes or look on the internet. This is an easy way to represent such an iterated map. And for this family of functions, we can check what are the limit sets. So the limit sets are obtained when you apply m time to an initial condition x0, and you let m goes to infinity. You look if you converge to one point or to something which is periodic or periodic and so on. And you can plot it as a function of r. And there is this famous picture where you have first only one fixed point, then two fixed, a periodic, but of period 2 point, but an orbit of period 2, and then 4, and so on. And then it's more chaotic, and there is a picture in the notes. And I mentioned this is period doubling bifurcation. I want to be more precise today, but in order to be more precise, I had to say something about bifurcation. So I just introduced a few things about this last week. I define what is a structurally stable function. So please check the definition. I cannot recall it, but it has a very precise definition. If you perturb in a certain sense this function, the system that this function generates doesn't change so much. So this is a notion of structurally stable function. But of course, if a function is not structurally stable, it's structurally unstable. And this is where we can see bifurcation. And just at the end, I said something about this setting. We expect, and we will see it today on a simple example, that when you have a bifurcation, it can appear only if the Jacobian matrix of this function, or okay, I don't need the R here, it's more general. If the Jacobian matrix of this function, so this is just a matrix, we can compute its eigenvalue, and we are going to say that if now it depends on R, we can have a bifurcation at R0 if when you look at this function of two variables, the variable R and the variable X, the eigenvalues of this cross either this set of complex number which real part 0 or the set of complex number of modulus 1. This is in the discrete time, this is in the continuous time. So if at a point R0, X0, you cross exactly one of these two sets, you can have a bifurcation. So we will see it again today in exactly in this setting. So I spoke a little bit about the general theory, but it's quickly very complicated. So I want to come back to this logistic equation because we can learn quite well. If you have any question, you can ask me at any time. Okay. So let's continue. I'm back to the logistic equation. I want to understand what exactly happens here. This is a new section which is back to logistic equation. This is 7.5. But now we have additional privileges. And there is one theorem which I like very much, and I will recall it. It is this implicit function theorem. If you have not attended calculus 2, it will be new. If you have already attended calculus 2, it's a nice, it should give you a nice souvenir about what we have seen. So we are going to look at this pair doubling bifurcation, and we have to look at this theorem, which is called bifurcation. Bifurcation theorem. So I want to study exactly what happens here. So in this example, this R is one-dimensional. So it means it's a parameter on an interval. If you have more degrees of freedom, so if your system depends on more parameters, of course, it's more complicated. So we consider an interval R, an interval in R, and we consider it open. It's always simpler. And I consider a function of two variables. So it's a function of two variables. On this variable, it's going to be small r, and this variable here is going to be tiny x on the real line. So I will consider this function as a function of two variables. This is a function of two variables seen a bit differently, because I put the second or the first variable, I put it here, but I can look at it as a function of two variables. So I assume that it's differentiable in both variables, and because this is the setting. And now I suppose something. Suppose that we have one point R0, X0 inside this interval time R, so that f at R0, X0, so if I can write it with two notations, please be aware. Usually, function of two variables, you will write it like this. I'm just writing this as a parameter because these two variables do not play exactly the same role, but it's the same. And I assume that this is that X0 is a fixed point, so we have this equality. At X0, for the parameter R0, we have a fixed point. And I need to have one more condition. I need to assume that f prime at R0 is 0. Now you can say, oh, what is this prime? Because we have two variables. It's the derivative with respect to the second variable. So it's dx Rx evaluated at R0 is 0. I assume that this is different from 1. The implicit function theorem, usually you have to assume that it's different from 0, but you will see here it's natural to assume that it's different from 1 if you look at the proof. Then probably I should do a picture of this implicit function theorem, just to remind you what it is. Perhaps in calculus, you have a complicated curve. And you have one point which satisfies a certain condition, which is exactly this one. We can not directly see it on my picture, but it's going to be something of this type. You have R and X, variable X. And I assume that a certain derivative is different from 1. And then the implicit function theorem tells me, oh, you can find a small interval and describe this complicated function as locally as a not normal function. So you have a phi, which is a function on this interval, which describes this. So this is exactly what I'm going to write, but this is a precise formulation. Then there exists an epsilon bigger than 0 and an interval I epsilon with what is this I epsilon? This is R0 minus epsilon, R0 plus epsilon. So this is this interval I epsilon. So there is such an interval. And phi, which goes precisely from this interval to R, so that first phi at R0 is precisely this point is 0, is the point 0, and phi of R is equal to f R of phi. So it looks complicated. What does it mean? Remember, I'm looking for fixed point. So it tells me, oh, this phi of R, so these points are also fixed point locally. So it tells me exactly phi send me on the fixed point. So I can describe all fixed points close to this x0 at R0. So we have one fixed point, and this implicit function theorem tell me, oh, you can describe all fixed points locally when you change slightly R and slightly X. Okay, so this is a fixed point equation. So phi maps R0 to x0, and all points near are fixed point.
The R is phi R is in I epsilon, right? But is I epsilon in I?
Yes, I didn't mention that. Yeah, the I is that's why I took it open. And R0 is inside, so you can always find a small interval. And this is for all R inside this interval I epsilon. And there is always a second part in the statement of an implicit function theorem. In addition, all solutions of the equation x is fr of x close to the pair R0, x0 R of this form. And what is this form? It means precisely this form here. But this is the implicit function theorem. you have done calculus 2, you should remember something of this type. If not, it's going to be a nice theorem that you will see in calculus 2. So keep it in mind what it means. We have one fixed point for R0, and the fixed point, I call it X0. And I'm claiming with this theorem that if a certain derivative is not 1, you can look at the proof. I gave the proof because it's a nice short proof. Why we have this one? If this derivative is not 1, we can find all points which are also fixed point close to this pair X0. Now R0 is 3. This is a fixed point. So all of them are described like this. But it's going to say something. Do you have any question about this?
How can this theorem tell us anything about bifurcation?
I'm going to say it, of course. Oh, you can already guess. 1 is quite special. In the set of all possible real values, 1 is quite special. So it already tells you that this happens quite rarely. Generically, it's different from 1. This is the first thing you can observe, but it says more. Now, if we consider, so this is, the theorem is ended. But if we consider now precisely a f which is C1 of I times R, and also in this framework, a bifurcation can take place. Okay, I should say a bifurcation with one parameter. Not doing the most generous theory with one parameter. Why? Because I'm considering the parameter only in one dimension. One parameter can take place only if f prime at R0 X0 is equal to 1. Because a bifurcation is a significant change in your, remember this picture we had. When I mentioned bifurcation, I said it's a significant change in the behavior at a certain point of the parameter. But now, if the value is different from 1, we have something very continuous. The set of, we are in this situation. Here we have no bifurcation. Everything is continuous. A fixed point is just moving along this curve. So in order to have a bifurcation, you must have f prime equal to 1. It's not necessary and sufficient, but it's necessary. Okay, for a bifurcation of this type. Again, I'm not in the most general situation. Okay, so we are going to use this information to study the picture I mentioned, a period doubling bifurcation. So now I come back to the logistic equation. So or in fact, it's more general. So let R0 belong to I, so that we have two things. Now I consider FR squared. So I'm considering I want to analyze this situation. So if this is a period 2, it means it's a fixed point for f squared. So I consider this, and I assume that this equation with the 2 has a solution. In fact, has two solutions. Has two solutions for R bigger than R0. And what are these two solutions? I call P plus of R. I call this X, and I call P or P minus. P plus R is equal to X of X. Why? Because if I take this value, it's not a fixed point. If I apply f, I get here. But when I apply f again, I'm here. So these 2 points are fixed point of this equation where you apply 2 times. So I call one of them p plus or p minus of r. This is still the parameter r. And the other one is p plus of r. Both are solution of this equation. So I assume that we have this on the right of R0. So I assume that I'm in this framework, but also in that only in that, sorry, or in that for R smaller or equal to R0, only the equation FR of x equal to x as the solution. What do I mean by this? Of course, this solution is a solution of f squared. Because if it is a fixed point, you can apply it 2 times, it's still a fixed point. But what I'm saying, we don't have 2 solutions like here, so it means f squared has no solution, except the one which is a fixed point. It has no solution, not 2 different solutions, let's say it like this. We are exactly in this situation. Above R0, we have 2 different solutions. Below, so it's solution of this equation. Below R0, we have a solution of a single solution of this equation. But of course, this solution is also a solution for this one, but you have only one. So we are in this situation. And now I want to study a bit this situation. So from the theorem I mentioned before, this function f squared has a bifurcation. So by the previous theorem, f squared has a bifurcation. It has a bifurcation at R0 because nothing happened on the left and something happened on the right. And then, so if I compute the derivative of f squared, I take this derivative and I evaluate it at R0 is 0. Sorry. What is x0? X0 is this value here. So x0, I call it R0 of x0 is x0. So it's exactly this fixed point. Then by the theorem, this is 1. Because we have a bifurcation for this function. And now I compute. This is a composition. Remember, f squared is f composed with f. So f squared at a point x is f of x. This is the definition of f squared. So I take the derivative of a composition. It makes f prime R0 at f of x0 times the internal derivative, which is f prime at x0. Right? This is the derivative of a composition, but this one, by definition, is x0. So we obtain this is f R0 prime at x0 squared. You have 2 times the same thing. So it implies that this f prime R0 at x0 is minus 1, no, or 1. Because the square is 1. So it means that we studied this function. Here we have a bifurcation of the function, which is a square. So by the previous theorem, it means its derivative at this point is this derivative is 1, and I do the small computation. I obtain that this 1 is this square product of the numbers, so it means we are in 1 or minus 1. So it means the function here, exactly at this point, has either a derivative 1 or minus 1. That's it. That's what it tells me. Do we all agree with this? Function.
But that's when you take the derivative. Why is there no factor of 2?
Be careful, it's a listen, it's not a square. This notation, it's a composition, it's an iterated map. So I wrote it here. Now, when you differentiate a composition, okay, I agree this is misleading. If you're in calculus 1, when you write this, I would not agree. But the meaning here is we are doing an iterated map. So F2 means we apply F 2 times. It's exactly this. I don't have a better notation. If you find a better.
On the left corner.
Sorry?
Rather on the left corner.
If I put it here, you will not be happy. If I put a parenthesis, you're not happy because this is a derivative. In fact, the best notation would be this. But it's a bit complicated. Yes, because it's a composition. It's 2 with the composition. Okay. If you find something better, tell me. Okay, we are in this case. And now there's something I don't understand. So we call a period doubling bifurcation. So this is what I can now define bifurcation. This situation, so what means this situation? I don't want to revert it, but it's this one. Okay. It's exactly this, what I mean by this situation, which I have described here. And so that f prime r0 at x0 is equal to -1. So be careful. With this result, I can only say my f prime r0 x0 is either 1 or -1. We call a period doubling bifurcation the case when it's -1. So what does it mean? It means that the function here is not singular. In fact, it continues. Because with the previous theorem, -1, it's not 1. So it means I have a continuation of this by the implicit function theorem. So it means in this case, inside these two branches, we have a continuation. So we have one fixed point. It's a repeating. So it's not attracting. Whenever you are not exactly at this point, you move away, but it still exists. And there is I don't fully understand, but apparently this is almost always what happens. I wrote something, but I don't like it so much. If somebody wants to understand or to work a little bit more why we cannot have one, I would be interested. This is a slightly more advanced exercise. Why the situation 1 cannot take place? I'm not sure I understand.
Professor, so in this situation, then for r greater than r0, then the fr square of x equal to x has 3 solutions.
So it means indeed it has 3 solutions. Yeah. But this one is unstable, and these 2 are attractive. So it means you would move to these 2 points. And in fact, this is one argument why there is a unstable solution is between these two attracting regions, you have a separatrix. And yeah, you need to have a point which is unstable, but in between. But you're right, it means there are three solutions. Yes, but one is also, in fact, a solution of a smaller. So it's a fixed point of F. And remember, when I defined a two-periodic solution, I said we don't want to have something smaller. So it's a fixed point is a one-periodic point, so it's not a two-periodic point with the definition I gave of a two-period. So there is no contradiction. Okay. So as I said, the case equal one, apparently we can always eliminate or rule it out. Okay. And this equation is good because remember what I said just at the end of the reminder, because here I said we have a bifurcation when the Jacobian matrix cross for this three-time system cross the unit circle. But look, in one dimension, this is the Jacobian matrix as a function of one variable. The derivative, if you have only one variable, is a Jacobian matrix. And I'm just saying that, yes, it cross at R0, X0, the unit circle, because it takes the value -1. This is a point in the unit circle. So there is no contradiction with what I said last time, that we have a bifurcation when the Jacobian matrix, one eigenvalue cross the unit circle. This is exactly the case here. And there is a remark in the notes, I don't want to write it, but then we can have a second doubling period bifurcation with a solution. We would study F4 of X, also F4 with the parameter X, the parameter R, and look at solutions of this equation. And we would have a new something of the same type here. But now you would compare it with F2 instead of with F. So we can iterate the process. It's an iterative process.
And period doubling not happen at F3.
F3, no, not with this phenomenon. This is period doubling. F3, I will mention it, but this process, no, doesn't equal F3. But you may have a solution of F3, but you cannot reach it by this process. Good point. But now there is something I want to add, which is very nice. And okay. So let me just move to something else, which is called Tchaikovsky ordering. So the first observation, what I want to tell you is, in fact, if you have this picture in mind, after a couple of bifurcation, you have plenty of points in between. So we will see in the following theorem. But there is first an observation, which is a bit surprising. No, it's not surprising. Any integer, positive integer, so any element of n, let's say n star, because I don't want 0, can be written as 2 power m times 2n plus 1. I'll let you check. Take any positive integer. You can always factor a certain number of power of 2, and then have another number which does not contain a multiple of 2. So any number can be written like this for n and m to natural numbers. You just check this is true. If you attend a course on basic number theory, probably this is a baby observation. So we define ordering, we define what is called there are different way of writing it. Tchaikovsky the Sharkovsky ordering. So I'm going to order. Yes.
You know, or about the statement you made before.
What is the problem?
So if it means for one parameter settings, the application always occurs simultaneously.
No. Okay, I see your. I don't know the answer to your question. I don't know. Okay, yeah. The question is, in fact, I don't know. Do we have? That's why I consider only this case. But when we have a period doubling here, does it appear simultaneously here or not? I don't know the answer. I didn't check carefully. Okay, so if somebody wants to check, when we have the question is natural. When we divide one step further, does it appear at the same time, or do we have this? And for example, this. I think both can happen. But I think it's still meaningful to compare, because remember, this point is not a fixed point. You alternate here. So it means if you know probability they appear simultaneously. Okay, if somebody wants to check this picture, but I think no, they have to appear simultaneously. I'm not sure, but I think so.
So if they don't appear simultaneously, then we have to consider actually.
Find a good question and find a good answer. I don't know the exact question. Now, there is a tricky question. You can wonder, does it appear simultaneously or does it appear not simultaneously? I suspect that it has to appear simultaneously, but I'm not sure.
One parameter.
Maybe we are discussing only one parameter. So let me continue. I define an ordering of all integers in the following ordering. So it's not an inequality, it's a curly inequality. Okay, and you continue. You observe that this here I consider only m is equal to 0. And then I put all these numbers. And I can continue to infinity. And then I consider 2 times 3, 2 times 5, 2 times 7. And you continue this. And you observe that these numbers are for n is equal m is equal to 1. Yes. Then you continue. And then you have 2 power n times 3, 2 power n times 5, 2 power n times 7, and you continue. This is for m is equal to m. And you continue. And you just miss some numbers. Sorry, Professor. Wait, I finish my sentence. I miss some which are 2 power 4, bigger than 2 power 3, bigger than 2 power 2, bigger than 2, bigger than 1. And these are obtained for n is equal to 0, which I did not consider before. I consider n is equal to 1, 2, 3 all the time, but I miss the case n equal to 0, and I put them here. So you can check if you do this systematically, you cover all positive integers. But I put a certain ordering, which is called Sharkovsky ordering. Yes?
I thought you were doing prime numbers and then 9 appears because 3 times 3.
Did I speak about prime number?
No,
No, I didn't. I'm speaking about all integers.
Odd number first and then.
No, there is no odd number. Oh yeah, odd numbers first, but yeah.
And
then
you add subtraction.
yeah. You can check, you have all of them. This is just a different ordering. There is a weak point. The weak point is already here. This is 6 or 10. Any of them here is already after infinite number of other numbers, which is more complicated than the usual ordering of numbers, because many times we have an infinite number before. I mean, before one, you have infinitely many.
Is there, I mean, I guess this is a lot of stuff, but is there like the n, it's a decreasing power too, and we could have like, if we wanted to be regular, we would have put 1 first and then 2.
It's not, I want to put them in order. It's the one which is needed in the following statement.
Okay,
It's not my choice.
yeah.
Maybe it's this guy's choice, but it's not mine. Don't blame me. So what is the theorem related to this, which is nice? It's a nice statement about this period doubling. So it's called, you can guess, Sharp's theorem. It says, so if we consider f any function from m to m, but it's a 1D system, so it means this m is a subset of R, so it's a one-dimensional system. If f is continuous, and has a periodic orbit of period n at certain integer. So what does it mean? It means we have x, there exists an x such that when you iterate f n times, you get the same x. This is a periodic point, n periodic point. And this x has to belong to I, otherwise there's a problem. So if we have such a function which has an n periodic orbit, then it has n prime periodic orbit for all n prime integers, such that n is bigger with this curly than n prime. So it means if you have a system of period 3, because you mentioned 3, in fact, you have a fixed point of or n periodic point for any integers.
And start.
And prime.
All right.
So if you start with okay, take let me start here. Oh no, let me start here. If I have an 8 periodic point, automatically, oh no, this is 16. If I have a 16 periodic point, automatically I must also have an 8 periodic, a 4 periodic, and a 2 periodic, and a 1 periodic point. The system forced me to have so many points.
So the period capital N in N star, right? Mhm.
So if we take any n, then n prime, yeah, n prime is also an integer.
Like
Yeah, but
integer
like,
star because you want the Shapovsky ordering, which is in
Okay. Yeah, but in,
good point.
okay.
And prime too.
No, I don't need it because it's, okay, it's not in my list. So thank you. That was important. We don't, what is a 0 periodic point, by the way? It's not defined. A 0 periodic point, a 1 periodic point is a fixed point, but a 0 periodic point does not exist. That's it.
So the n.
Okay. But my n contains zeros, okay. I need to put this.
In the textbook, you said that in the notes, you said that n is bounded and closed also.
Possibly. Sometimes I'm a bit more precise in the note than on the blank sheet. Yes. Okay. Yeah, the notes are always a bit more precise. It's possible that I omit some assumption, but yeah.
Answer.
Yes.
So this theorem implies that if the system has a period 3, then it has a period.
Corollary. if the system has a three periodic orbit, it has n periodic orbit for any n star. Yes, this is true. If you have a system with a three periodic orbit, automatically you have all the other one, and they are different. I mean, the number 6 is really a periodic orbit of period 6, which is not a point which is three periodic. It's a point where you need to go 6 steps in order to come back. In my definition, a 6 periodic orbit is not a point which is a three periodic orbit. So you have all of them.
So this may answer the question I asked before. So maybe they have to occur at the same point because otherwise you don't have, right?
Okay, I don't know. I told you I haven't set a good question, so you can ask the question, fix the question, and find a good answer. Okay, so this is the corollary. Of course, it has been discovered before. Sorry for you. A remark about the logistic. So this is general. It's not only for the logistic equation, but for the logistic equation. The logistic equation. At least there are two values where we can check f has an orbit of period 3 or r equal to 4 and r is equal to 1 plus 2. I'm not claiming that these are the only values. Not at all. I'm just claiming that you can check. So what does it mean? It means there exists a solution of f of f of f of x is equal to x for this specific r. But because this is the solution for Rx3. Be careful, it's not so easy because f, remember f of r of x is r times x times 1 minus x. So when you so it's a polynomial of degree 2. So when you iterate, you are going to get a polynomial of degree 6. And you 8. Yeah, okay, even 8. And usually a polynomial of degree 8, we cannot find its solution explicitly. So I guess with these numbers, it's a bit simpler. I didn't do the exercise. So if somebody wants to try to check that we can solve this equation. Or do some cobweb plot and check what happens. The cobweb plot for F3, you write the equation. No, you just do the cobweb plot for these two values and check what happens if you converge to an orbit of period 3. That would be nice to have a picture of this. But it means we will come back to 4 because 4 is chaotic. We will prove it later. It means for I is equal to 4 or I equal to this value, you have an orbit of period n for any n. Because period 3 implies any other. So it's an interesting result. Now, the proof is partially given in the reference book. And for the full proof, you have to look elsewhere. So it's not completely trivial. but it's an interesting result. Okay, is there any question or remark? I know it's quite dense, but this is quite usual for us now. Let's speak about chaos. Don't expect to know everything about chaos, simply for one reason. There is not a single definition. There are plenty of definitions depending on the context. And I'm going to stick to several definitions. And essentially, there is a big difference between discrete time and continuous time. And you should feel it by now. For the discrete time, the equation is x of m plus 1 is equal to f of x of m. This is a discrete time equation. For continuous time equation, we have this. Here, I mentioned it several times. Essentially, you can compute it. You have the flow. If I give you f and xm, you can compute the next one. Here, no, because it's a differential equation. The flow, remember, is given by the function phi. And this phi is a function of t and x0. You don't see the f anymore in this formulation. I mean, when you solve this equation, the f is hidden in the phi. So the discrete time system is much simpler in a sense than the continuous time, because we have access to f directly, while here you need to solve this differential equation, and f is, of course, it's hidden here, but you don't have directly access to it. So I'm going to give a definition of chaos for discrete time, but some part of the definition works also for continuous time, but it's much more explicit on discrete time, and it's already rich enough. So please feel the difference. I already mentioned it 1 week ago or 2 weeks ago. There is really a big difference between these two equations. Here you can see the f. Here, when you compute the flow, the f is hidden. So I'm mainly considering discrete time system. But we have seen with the logistic equation, many things can already happen. So let me remind you the notion of topologically transitive reminder. Oh no, it's not a reminder because we introduced it for continuous time. So let me introduce it for discrete time. We consider f from m to m. If I come back to the general setting I'm in now, this is just a metric space. But you can think about, if you don't want to be in this generality, you can think just about Rn. Rn is an example. So you consider f from a metric space to itself and generating and iterating by the equation, just to precise it. X n plus 1 is the f of x7. This is an iterated map. Okay. We say that f is topologically transitive. It's very similar to the continuous time, but the continuous time precisely was expressed in terms of the flow. Now I don't need it. F is topologically transitive if you remember the definition of topologically transitive. It was take two sets and move one of them with the flow, and it should at a certain point cross the other one. This was topologically transitive. It means it mixes any two sets after some. So in the discrete time, it's exactly this. It's topologically transitive if for any U and V open set, the M and non-empty. Okay, it should not be empty. The empty set is open, but I don't want it. So U and V open set M exists M. I come back to G, but G, remember, it's simply either N or Z. So that what we apply F M time to one of them, and its intersection with the other one is not empty. We iterate, we apply F M times to U, and at one point it should have a non-empty intersection. This is a notion of topological determinism. And remark, because I made this remark with the other context, if the metric space is in Rn, so it's not the general case, but if it is in Rn, then F is topologically transitive, if and only if there exists a dense orbit. What is a dense? What is an orbit? An orbit is a set of Fm of x for all m in this group or in the Smith group. And what means dense? I have added a more precise definition in the notes when I introduced you the first time. Suppose this is M. A dense orbit is difficult to draw it. Means we go close to any point. It's difficult because I cannot intersect. An orbit cannot intersect. So if I want to go closer now, I need to be very careful and so on. But a dense orbit means no matter which ball I take, the orbit will go inside. This is a dense set. So take any small ball, after a while, your orbit will cross it. This is a dense. So in any ball, you have one point of view. Okay? This is a dense set. In fact, I should not make this continuous because it's discrete, but if I just draw points, it's not. So this is a notion of topologically transitive. And remember when I defined attractors, it plays a role because we cannot decompose further a transitive set. You cannot extract because you cover everything. You cannot decompose it into two parts. So we use it when we define the notion of attractor, and we will use it again. So this is, I recall the notion of topological transitive. There is another notion which is usually associated with chaos, but it's not a basic object. We will see another notion related to chaos, which I haven't defined yet, is sensitivity to initial condition. So I will explain what it is. Sensitivity to initial conditions. What it is. Probably you heard already about this. It's this idea that if you start with two initial conditions which are very close, you let your system evolve. Again, I do it continuously. Even though they are very close, they will move away from each other. This is this notion of sensitive to initial condition. So now I need to make it more precise. what do I mean by this? And I cannot say that the distance is becoming bigger and bigger. This wouldn't fit, because suppose I am in a box. Even I can define this notion of sensitive to initial condition, but suppose I'm in a box, even if they start very close and then separate, the distance cannot become very big if I want to stay in this box. So I cannot just say they move apart with an infinite distance. This is not a good notion, because in a box, you cannot go forward. So what is the notion of sensitivity to initial condition? So for F, what it means? It means there exists a delta bigger than 0, such that, so I need to write it completely and then we can discuss. Such that for any x in M and any epsilon bigger than 0, there exists a y in M, which is at a distance, but there exists a y in M in G, so that the distance between x and y is smaller than epsilon, and the distance of Fm of x, Fm of y is bigger than delta. This is, so let's think about it. This is the notion of sensitivity to initial condition. So I'm saying there exists a delta. This delta, you can think about it, the maximum size of your box. You cannot have a distance bigger than the maximum size of the box. This is impossible. But there exists a delta, so that no matter which x you take, no matter which epsilon you take, you can find a y which is at a distance. I'm in the metric space, but if we are in the Euclidean space, this is just a Euclidean difference. But I'm just in a slightly more general setting. But the distance between x and y is smaller than epsilon, so I can take x and y very close, but there exists the m large enough so that when I iterate this x and I iterate this y, the distance becomes larger than delta. So if I fix my delta at this distance, this is the maximum distance, it means no matter, and I take any x, I can find a y which is at a distance epsilon, but after some iteration, the distance will be bigger than this delta. That's the meaning of initial sensitivity to initial condition. So think about it. It's not that the distance can go to infinity because maybe I don't have this space, but there exists a delta that no matter how close I start with respect to x, then after some m, the two trajectories are at a distance bigger than delta.
But this behavior could be non-chaotic behavior as well.
Yes, very good. Indeed, I said this is notion related to chaos, but you cannot take it as a definition, which sometimes can be done, but because we have a think about the simplest function, it has this behavior. The linear function has this behavior. Observation. So this is very good observation. Be careful. This cannot be used, or you cannot be used only this for the definition. For chaos, which I haven't defined yet, since this is an easy exercise, you take the function f, r to r, x goes to 2x, which which is not very complicated, and probably you will not say that this is a chaotic function, satisfies this, sends it this property, this sensitivity. Elimination condition. Check that this definition is satisfied by this function. So indeed, you should not take this just as a definition of a chaotic map, because then this function would be chaotic, and this is probably not what you want to see. Okay, so I now need to give a definition of what is a chaotic map for an iterated map. And in fact, it will be a corollary. Let's see. And then we are going to check that at least one example, we can clearly check that it's a chaotic map. So definition. There is one name which is attached to this definition because he didn't say exactly this, but he's the first guy who proposed this, essentially this definition. So let M in a metric space, yes, you can think about N space and F from M to M continuously. By the way, nobody asked me, but what is continuity in a metric space? Okay, it's not the point, but if you think about Rn, you know what is continuous. In a more general framework, I haven't given a definition of what means a continuous function from these two things. But you have balls, so you can still do it. So, but this is not important. You have a feeling of what is a continuous function. Then, and many things can be just understood with feeling. The iterated map defined by F with chaotic. If there are two conditions, if F is topologically transitive, which we have just seen, and this is quite surprising, it possesses a dense set of periodic points. Which I have not exactly defined. So first let me, what is a periodic point? It's a point which is on an n periodic cycle. So a periodic point is a set of x, a set of n periodic points for any n. So take the 2 periodic points, the 3 periodic points, the 4 periodic points, and so on. And so the second condition means we possess a dense set of periodic points. So this is M. It means no matter which ball you take, again, I'm explaining what is dense. No matter which ball you take, there exists a point inside which is n periodic for some n. This is a notion of the dense set of periodic points. So in the set M, any ball contains at least one n periodic point for some n. So it's a bit surprising that this is a definition of chaos, but in fact, this is the point. Transitive, topologically transitive means you cannot decompose it. So you cannot find a part which is simpler, which has a, you want to isolate it. But simultaneously, it says that in the set M, everywhere you have some periodic points. This is the definition of chaos. And I gave an exercise about this notion of periodic points, a map which contains plenty of periodic points. Now, what is the relation with the set of sensitivity to initial conditions? So it's a lemma.
Is it equivalent to say it's 3 periodic in N star?
Say it again.
Like instead of N periodic points N in N star, can we say 3 periodic points?
Oh, you really want me to put in N star? Okay.
No, it's 3 periodic in N star. Because then if you have 3, you have everything.
No, it's not equivalent. Because I'm not saying that, for example, you could have dense set of 2 periodic points. It's not for all N. I say for some N. So it means in any ball, I could have only a 2 periodic point. I'm not saying that you have all periods. It's not the same, no. I don't know if you can have only 2 periodics. Probably it's possible. I don't know, I don't have an example, but you're right. If you would have, but no, even if you had 3 periodic, of course, if you had 3 periodic points, you would have all the other one, but it's not automatically dense or whatever. So no, it's just take the definition as it is. You have a dense set when you consider all periodic points, no matter what is the period. So what is the lemma? What is the relation with sensitivity to initial condition? So if we consider N a metric space, which is not finite, not only a finite number of points, and F from M to M continues. Then if F defines a chaotic, if F defines a chaotic iterated map, then it has the sensitivity to initial condition. So it means we don't want to take it as a in the definition of chaotics, but you get it for free, which was not what this guy had in mind. I think at the time he put the 3 conditions. He put the condition topologically transitive, dense set, plus sensitivity to initial conditions. But somebody proved that in this setting, you automatically have it. You don't need it. So these 2 conditions are sufficient. You have the 3rd one for free. So what is the next? So now we have a definition of chaotic for iterated map. And again, for continuous time system, this notion of topologically transitive is also necessary. We already mentioned it in the continuous time setting. The notion of sensitivity to initial condition often appears. I'm not sure that, I know this notion of dense periodic point does not exist in the continuous setting because you have orbits. So do you need to replace by dense periodic orbits? I don't know, but okay. We discuss for now only the discrete time setting. But they can be adapted to continuous. So what is my next aim? I want to show that at least one we can show that at least one function is chaotic. So aim is to show that the logistic map F4 is chaotic. This is the aim for this, the end of this section. We will not be able to fully do it today, but I want to show this. So at least F4 satisfies these two conditions. So for this, we will go through, we will introduce a new function, and we will finish the job next time. So we introduce, and it's a nice example. We introduce what is called the 10th map. This is the official name. Choose the 10th map. So we consider the following function T mu from 0, 1 to R, given by T mu of X is definition mu over 2, 1 minus, so what jobs mu is any real number. So it's a rather simple function. If you draw it, if I draw T2, this is T2. Because of the absolute value, it has this shape. This is 0, 1. And the maximum of T2 is at 1. It's symmetric. So this is T2, but you can generate this for. So if you think about if you have in mind the logistic equation is more like this. Now this is a bit simpler because it's linear, except that you have these two regions. That's why we start by studying this one, and once we understand this one, we can say something on F4. So we study this, which is called the 10th map. I don't know why it's called like this. Maybe just because of the shape. Okay, so we consider now first mu is equal to 2. We will need other mu for the next section, but for this one, I consider only mu is equal to 2. So if you want to get rid of this absolute value, you can. This is going to be 2x if 0 is smaller than x smaller than 1/2, and you are going to get 2 minus 2x if 1/2 smaller than 8 smaller than 1. So I can eliminate this absolute value by considering two cases. So it implies that T2 is in fact from 0, 1 with value in 0. So I don't need to have here. This is useful for more general mu. And now small computation for you. What is T2 M? So when you iterate this M times, then it turns out that there is an explicit formula. I give you some formula. I would be happy if somebody prove it. Probably the proof can be done by iteration. You prove it for a certain M, and then you prove it for induction for the next one. I think this is the easiest way. So the solution is 2 power M. I hope I don't do any mistake when I talk. I double check what is in the notes. In the notes, it should be correct. So you have a certain, I will say who is J, and you have another expression 2J plus 1 minus 2. Not sure you have to copy exactly the expression, but lines and lines. 2J. So what is this? We have two expressions, but I haven't. I need to say who is J. So for J belonging to the set 0, 1, 2, up to 2 n minus. So what does it mean? It means we divide, in fact, 0, 1 into very small intervals. And each of these intervals is of size. The size of each of them is 1 over 2 power n. So we divide, and when I write this, I just run. So for j is equal to 0, I'm in this interval, j is equal to 1, I'm here, j is equal to 2, it's like a partition. And I'm claiming you can compute Tm and have these simple expressions depending in which interval you are. So look, you are inside an interval. So if you are inside, in fact, if you are in half of one interval, you have one expression. If you are in the second half, you have a different expression. And this comes simply because you have to iterate this on either you're on the left of one half or on the right of one half. So, okay, it's a small computation. But I have something explicit. I haven't done a mistake. So again, these intervals are of size 1 over 2m, and I'm claiming that each of them contains a fixed point. And this is also a small exercise. And if I define x, which is equal to 2j over 2 power m minus 1, this expression or this point, I'm claiming that it is in. Oh, sorry, I forgot some. Okay, no, that's not right. 2j over 2. So I'm claiming that this point is inside the j's interval. Let's say this is this one. And that Tm of x is equal to x. This is a computation you can do. This is easy. Checking that its fixed point is easy. T2, we are dealing with T2. So what does it mean? It means I understand what happens for each of these intervals. I have an explicit expression. And inside each of them, I have a m-periodic point. This is a m-periodic point. Oh, what does it tell you? If in each small interval we have an m-periodic point, it means a set of periodic points is going to be dense. Because no matter which small ball, a ball in this case is an interval, no matter which small balls you take m sufficiently large so that you have one interval, and inside you have a fixed point. So this is what I'm going to write. And this thing implies that. So observation. So first, which I haven't written, but each interval, or subinterval, I should say, each subinterval is mapped. This is something you can easily check. Each subinterval I have, this is what I call one subinterval. Each subinterval like this is mapped to 0, 1 by t power 2 to m and possess m periodic fixed point. And now, since each interval or subinterval is of length, what I just said, it's of length 1/2 power m, we get, well, the set of fixed points is dense in 0, 1. Because in each subinterval, we have at least one. The set of fixed points is dense. Fixed point is dense in 0, 1. So please understand the argument. You don't have to remember the details, but I take 0, 1. I subdivide it into small intervals. I can check that each small interval is mapped to 0, 1 when I apply TM. And I can check that each subinterval contains a fixed point. So it means no matter which, now choose a certain interval, take m sufficiently big such that now we have one interval, one small interval inside. This small interval contains a fixed point. So it means for any ball interval, we have a fixed point. That's it. That's the density of fixed point. So one condition is checked. T2 has this property of dense, a set of dense fixed points. The second property we need to check is that it is topologically transitive. So I will just quickly show that. We'll show that T2 is topologically transitive, but you can just guess it with what I have written. So take 2 U and V inside 0, 1, open. Okay. So I take, let me take again, 0, 1. I take 2 it doesn't need to be an interval, but for simplicity, I take an interval. But any open set. Now I take my construction here, and I take m small enough. No, sorry, m big enough, so that we have one small interval in this is U, this is V. So I take m large enough so that this small interval 2j over 2 power m, 2j plus 1 over 2 power m is inside U for some j. One of them is inside. Okay? And now I apply Tm. Then Tm, what I just mentioned is the image of this small interval by Tm is going to cover everything. So it means Tm of U is everything, because it contains a small interval which goes already everywhere. So in particular, a bigger interval goes everywhere. I finish my argument. So it means this 0, 1 inter V, of course, is not empty, because V is inside 0. And so we check explicitly that it is topologically transitive. Yes?
Does it have to be topologically transitive for any open set UV, or just consider a UV, and in this consideration?
No, it's for any. The definition of topologically transitive is for any. And I draw an interval, but you know, in any open set, you can draw a small ball. And in this ball, you can manage to have a small interval. So my argument is true not only for interval, but also for any open set, except that, okay, it's different. So it means the conclusion of this is that T2 is chaotic. This is what we have just proved. We have an example of a chaotic system. We check the two conditions, and just next time I will show you that it implies that F4 is also chaotic. So the F4 is related to it's a logistic map. In the picture of the bifurcation, it's the last one. Remember this picture like this. And then you have some region which are less chaotic. And so F4 is the one here. This is also chaotic. So we will prove the last step. And then we will use this for defining additional sets, control sets and so on. Okay, it's done.